Welcome back. I'm going to be looking at the Kalman filter again and how we can control and stabilize a little platform really, and it's quite an interesting exercise. I found it, I learned quite a lot from it. I'm going to be using the MPU 6050. There's other versions of it. I think it's 65000 and the 6000 and so on. It comes in a little board you can get like this, so you don't have to solder such a small device, and it's I2C in operation. So we're using the myRio, which can read I2C, but you could use any processor you like, of course, to do the same thing. But I think you'll find that the myRio, or the Rio, is particularly suited for this kind of thing, because we can very easily get in and change variables with a really good GUI, a graphical user interface. So if you look at the orientation of this thing, that's the orientation like this. So the Y pitch is that, we call it Y axis that way, that's pitch, that's roll, and Z, that's the yaw in that direction, rotating. Okay, that would be heave, but we don't have heave. That would be sway side to side. Okay, if you had that as well. So I've made up this little device which probably could be better, because it's made just from standard off-the-shelf servos that you buy, the model ones. I've used the geared one, the metal geared ones, so they've already got feedback around them. But I could probably get by without feedback, because as you'll see, the feedback from this MEMS sensor on its own would probably be good enough. And I've got my little sensor there connected to the myRio, and I've got a program which I'll run in a minute, and there's my sensor. Now I've covered it in tape, because if I don't do that, it would get shorts on the metal on my thing. Now this device here, it moves. I'm going to turn this off because it's got power to the servos at the moment. It moves in this direction, and that's the roll direction, and it also moves in this direction, which is the pitch direction, what I've defined as the pitch direction, and it's kind of screwed down to this thing. It also does yaw, but I'm not using yaw at the moment. Anyway, put it back on again, and now as you see, I'm using, I'll just put my program up on the screen. There it is. I'm using the Kalman filter program that I used before, and the Kalman filter this time, I've got two Kalman filters, or rather a larger Kalman filter, one for the pitch and one for the roll action. So first of all, you'll see the horizons there, that's when it's level, horizontal, that's what we're really after. The other one you can see is at 45 degrees isn't. And you'll see the orientation of this thing. So you can imagine you could have something on the top here, like a plate or something, and put a camera on it, trying to make the camera steady. So as I move this sensor, let's move it that way, and it goes that way and that way, and I move it that way, it rolls, and of course it can go anywhere I like as I move this around. That in itself has got perhaps some interesting applications that people might want to use something like that for, the roll and the pitch. But that, of course, that'll stay in a particular position as long as I keep the sensor in that position. You'll notice that as I pitch it in this direction, the thing goes in the opposite direction. Of course, if I turn it around this way, then it's in the same direction. The reason I've got it done so that it's in the opposite direction, although I can easily reverse it in software, is that I thought to begin with, well, all we need to do is put this on the top of this guy here, and then we're home and dry, because what will happen is it'll stabilize itself, and then it'll just sit it. We'll put the set points for each of these to 0, but you can see straight away it doesn't like it. It goes immediately into some kind of oscillation. When you try in any way, and it's not positive feedback, it is negative feedback, as you can see, because if I'm going in that direction, the pitch is correcting. So there's obviously more required than just putting your sensor and sticking it on the top of the your construction there. So just as I'm doing this, I can show you the Kalman filters output. They're really smooth. I'm still slightly concerned about the Kalman filters, although they definitely work for the pitch angles. I'm not convinced I'm getting out the velocities exactly as they should be, but since I'm only using the pitch, the angle and not the velocities, it doesn't really matter at the moment. So there's me rolling and that's me pitching. I can't use a 3D model, I'm afraid, because the myRio on the real-time processor doesn't support 3D graphics, that is, but you could actually stream it to the computer, to the PC, and I've seen people doing this in the National Instruments for something similar. So the question is, how do I go about putting the sensor onto this guy here and making it stable? So what I'm going to do, here's my system, is this. So I've got my signals from the MPU 6050, which is the gyro velocity, which is pitch, the accelerometer for pitch, the gyro velocity for roll, and the accelerometer reading. So this is velocity, acceleration, velocity and acceleration. Those go into the Kalman filter, and if you look at my other video in the Kalman filter, you'll see how that works. But although I've got one big Kalman filter here, in reality in the program I use two Kalman filters, and also I can say that they're not really Kalman filters, they're steady state Kalman filters, which is a Wiener filter. Somebody asked me on the reply to one of the videos, why am I calling Norbert Wiener, the famous engineering mathematician, Wiener and not Wiener? And the answer is, I believe that's what he called himself. That was how he referred to himself, because I do know somebody who actually worked in his team, an older gentleman that I've worked with for some time. Anyway, so the Kalman filter will give us out 4 signals, but I'm only interested in the pitch angle and the roll angle, and then I'm going to put that into PIDs, and then really just have a set point which is 0, corresponding to horizontal in pitch and roll, and then that'll give me signals out to the PWM, so the motors, and I'll of course have to tune the PIDs, and that's the only slightly tricky bit. You may be asking, why is he using PIDs? If you've got a Kalman filter, surely you can just do optimal control and linear, quadratic, Gaussian, or all the fancy stuff that we've read about in the textbooks. I'm not for 1 minute saying you couldn't use these methods, but one of the problems with ordinary state feedback is that there's no integral action in it, and you'll find in the papers that most people have to add integrators, integral action into ordinary state feedback to get it to work. Not that there's anything wrong with it, has its uses, particularly in multivariable systems. This is a multivariable system, but there's no cross-coupling between the two axes, thank goodness, otherwise that would lead us into all sorts of difficulties. So there's our set point, which is 0 in both cases. Of course, I can vary the set point as well. So, for example, when I get this running, I could set the, instead of setting it horizontal, I could make it some other angle and control the pitch and the roll. Okay, so move on to the second part of the video, which is putting the feedback around it. Okay, so I've now mounted with tape the sensor, the MEM sensor, and connected it to my mechanism. So the reasoning being that as I move the sensor, the mechanism itself will correct it. I should get 0 out. So, but what happens? The whole thing oscillates. You can see the output of the Kalman filter. So you can't, in fact, just connect it straight on the top. Even if I reduce the gain, what happens is I lose tracking ability, and it won't even stand up then. It just drops down. So I clearly need a control system to make it stable. The fact it's oscillating means I need some kind of phase advance, derivative action will do. I need an integrator to keep it vertical. If it doesn't have the integrator, it will flop over, just like an inverted pendulum or a Sedgway or something like that. If you didn't have the integrator, I say it would sort of be out by a certain angle, and I tried it and it's like way over here somewhere. It's useless without an integrator. And this is why state feedback on its own isn't much good either, because state feedback would give you position and velocity, so it'll give you the phase advance and position gain, but there's no integral action, so you have to add in integral action to state feedback to make it actually useful. The same goes for linear quadratic controllers. So let's try the final step. We'll put in a couple of PID controllers. Welcome back, and I'm going to be looking at something I've always wanted to have a go at, which is how do we make a mini stabilised platform, or a platform that stabilises itself. For example, you could have a ship, and the ship is moving all over the place, and you have an area which is level. It keeps itself level, like on the boat somewhere. Right, so how would we do that? So I've made up a little mock-up of this. Now this isn't necessarily the best way of doing it, of course, but it's a cheap way of doing it. These are off-the-shelf servos. I've got 3 of them. I've got one for the yaw motion, which moves in that direction, this one which is so-called roll motion, and this one which is the pitch. And so that can control this thing, and if I put something on the top, obviously, I would like it to balance it. In order to balance it, I'm using the MPU 65000, I think it is, which you can just see there, but I've got it sort of taped on, covered in tape, because I want to insulate it from the metal. That's the only reason. And it's a 6-axis accelerometer and gyro, and I've talked about it before, in fact, in one of the other videos. And I've got a Kalman filter for 2 of these 3 degrees of freedom, for the pitch and for the roll. The Kalman filter being necessary to get basically better estimates of the position. Of course, these motors have got feedback around them, the little servo motors, and I think in theory I can probably get rid of the feedback around the motors and just have open loop motors, and the loop is then closed with the gyro and the accelerometer sensor. But without more ado, I think I'll just show you a quick demonstration of it working. It's run from a myRio, and it's using the real-time processor. What you see on the screen there on the left-hand side is the roll in degrees. It's like an artificial horizon, and the pitch on the right-hand side. Now I could have had a 3D model, but you can't do a 3D model in the myRio real-time controller. You can do that on the PC. To do that, you need to stream the data of the positions to the PC and then draw it on the PC. So I'm not going to do that. So I'm just deploy it and see what happens. And you should see that it holds steady. Oh, it's a bit of it's settling down here. Right, so here we've got it now, and I'm going to move this platform. So I'm move out a little bit, and you should see what happens. You see that the top stays in the same position no matter where I move the bottom. Now notice I haven't quite got the stability absolutely right yet. I'll just move over to the other hand. I think it's easier to hold the camera on the right hand and move this guy. You see there it is staying up. Move it that way, it stays up. Move it that way, it's still staying in the right position. And although I can of course improve the stability of this, it shows you that it is in fact being controlled by a servo loop, and it's not just sort of somebody manually trying to make it stay vertical. You can imagine you could have a camera on there or something, and no matter how you move the bottom around, the camera stays in the same position. The other thing I can do is I can alter the set points on, in this case, the roll and the pitch. I don't have control over yaw, so I'm going to move that one. That's the tilt. Actually, that's in fact, when I say tilt, that's the pitch. So as I move it, I can of course control that. And you'll see the horizon moving there. That's the offset, to put it back, and I can do the same with the roll. So you can control that with a joystick, of course, as well. And I can't do the yaw at the moment anyway, not with this system. Put it back there again. It's got two Kalman filters to estimate the states. What happens when you turn the Kalman filters off? Oh, you can see. Not good, I've turned it back on again. Down here are the PID controls, which I just did myself. It's such a simple thing to do, PID. You don't really need to use special VIs. The only tricky bit is, of course, getting the scaling right. So I've got a control system to control the roll and one to control the pitch. And that's basically how the system works. I can, of course, just to show you that this is the case, let's increase the gain on the roll, and that should make it kind of unstable. Oops, there we go. You can see it's oscillating. For those of you who are interested in tuning PID controls, I've turned it down there. Let's turn it really low. So that would give us very poor tracking and very slow response. As you can see, it's very slow. We've got a low gain. I'll turn the gain back, the proportional gain back up again. What happens when we've got less derivative action is it should become more unstable. Actually not too bad at the moment. You can see it oscillating about a little bit. And so on. So, okay, so what we've got is stabilizing system controlled by two PID controllers with Kalman filters to estimate the positions of the roll and the pitch. I'd like to do the yaw, but I haven't got round to the yaw yet, I'm afraid. Some more demos to follow.